today we're going to talk about a little bit about evolution of verification in the FPGA world. Then we'll get to some, current best practices. So we'll start out, it'll be a little bit of a review, but then we'll pretty quickly get into current stuff. So when I do a live seminar, I always ask, who knows what this is? Sometimes not a lot of hands go up, especially anybody born after 1980 doesn't really recognize the vacuum tube. And before, say, mid-80s or so, this was really the basis of all electronics that, were designed up until the digital transistor took over finally in the 80s. At that time, all the way from like the early 1920s up through the 1980s, everything was really done by hand drawing schematics and then creating, this electronics. Even after we got some discrete silicon transistors, we still were designing, by hand, and most verification was done in the lab. Somewhere in the 80s is when the EDA industry took off, and we started to do those schematics and transistor diagrams and stuff. We started to do that on a computer, but for the most part, at first, it was still basically lab testing. And then at some point along the way, we began to do vector-based testing. So that was what I was calling the schematic age, and the testing was really a burn and learn verification. In the early 90s up to the early 2000s, that's what I'll call the hardware description language age. That was where we started doing our digital designs in RTL code, and we started doing our testing as kind of a test bench with maybe some vector testing still, but then we started writing procedural programs in that same HDL to do most of our testing. It was still a set of directed tests where we were saying, hey, if I give this stimulus, I expect this result, and I'll say that tests these features. So that in our little evolution graph was the next step. We started doing directed testing. Code coverage started coming in, where we actually, started doing the foundations of doing metric-driven testing. So code testing is just basically how well does my test bench exercise my code? And, have I covered all my lines of code? Have I covered all my branches, et cetera? And that was kind of a next little step. And then the first, big evolution came in what I'll call first generation hardware verification languages. So, if you looked at that traditional testing with directed tests, your test bench was probably written in that same HDL that you did your design. If you had a self-checking test bench, it would say pass or fail. And then the debug was where you started throwing waves in the wave window and doing some testing. So the first wave of what I'll call advanced verification was a few things to, take that to the next level. So the first thing was the concept of assertions and assertion-based verification. So assertions are basically taking what used to be built into our test bench and creating these little temporal assertions that we bind to our RTL code. So they might be just these two blocks handshake with each other, so I put an assertion there to verify the handshake. This is a FIFO. Let me put an assertion to make sure the FIFO is acting as I expected. I might create assertions for my state machines or just other logic. And the big change with assertions was that these are written in a language that is developed specifically for doing testing, for doing checking. That, because they were then bound to the RTL code, when I reuse this block in another design, all of those checks that I've written, because they're bound to that block, move along with it. And these assertions are temporal. So they have things like being able to say, when I see the request, wait 4 to 7 cycles to see the acknowledge. So a few benefits built in with these assertion languages. And those assertion languages also became the basis for what we call functional coverage as opposed to code coverage. So functional coverage was, I have this requirement, and I say, you know what, if these 3 assertions get activated, tested, and never fail, then that requirement is met. I have this requirement, and it's maybe these 2 assertions and this cover directive or this cover point. So these were things that you write, so it's not automatic like code coverage, but there were things that I write to say, you know, I am looking for this activity, I'm looking for this temporal relationship between these signals. If I see that, that indicates that some portion of a requirement is correct. So basically, for every requirement in my thing, if I create a verification plan that says I have these coverage objects, I can, you know, basically have a metric that says, have I tested all my functionality? If I get a yes, I'm done. If I get a no, I go back to my test bench. And then that's the last piece of these advanced verification methodologies was, instead of these being directed tests that are, I'm going to put this stimulus, I expect to see this result, and if that happens, then I say I've tested some feature. What I'm doing now is I'm doing randomization of my stimulus. So I'm not creating these directed scenarios. I'm doing a constrained random data generation. And then I'm depending on my functional coverage measurement to say I've generated enough stimulus that I've covered all of my objects. So, you know, for these hardware verification languages, we needed an assertion processing engine, we needed something that collected functional coverage, and we needed a constraint solver to look at the constraints I put on my randomization and create stimulus that obeys those constraints. So that first generation, all of these tools were outside tools. They lived outside of my simulator. My simulator was Model Sim SE at the time. My constraint solver, my assertion engine, was things like Veracity Specman, eventually Synopsys Vera. On the assertion language side, we had a language called Sugar, which eventually became PSL. So all of these first generation languages were living outside of my simulator. They were slow because they were having to communicate over the PLI. They were proprietary languages. So, you know, I had to make sure that those languages, you know, actually the concern was those languages being proprietary only ran on one tool. Only if that tool went out of business, your infrastructure business would go down. So there was a lot of concern, and that limited the adoption of these hardware verification languages, but it was our next step in the evolution, this first generation of advanced verification. The strange thing happened at the same time, though, was that while the ASIC world was still evolving, FPGAs really became commercially viable for like being parts that you would put into production. And so, you know, the first generation of FPGAs that were complex enough to use in production came along. But a funny thing happened is that a lot of engineering managers kind of looked at these and said, hey, these are reprogrammable devices. Why do we need to do all this testing on them? We can get stuff in the lab really quickly. And so they kind of abandoned a lot of verification methodologies for FPGAs because they thought, hey, we can just go back and put it in the lab. And I like to say that basically a bunch of people's chimp brain kind of reasserted itself. And we, in the FPGA world, we kind of went back to this burn and learn mentality. And that was probably like, right at the beginning of the millennium. A lot of that was going on, and it's taken a while for the FPGA world to start to, come back up this evolution tree and get into the same realm as ASIC verification. But kind of dropping back over there, that's where System Verilog, that first generation of those verification languages, is what really had the IEEE say, hey, this is good stuff. We need to have a standard for this, just like we have a standard for hardware description languages, VHDL and Verilog. They came up with the System Verilog standard, which took that Verilog language, and it did add some enhancements to Verilog just for RTL design. But it added assertions and functional coverage for the functional coverage stuff. It added the constrained random for doing randomization. And it borrowed a lot from the System C world or the C++ world and added object-oriented coding for, some infrastructure-based changes to the verification world. So once System Verilog was around, then, that was the tools and stuff, but there was still this idea that we needed a methodology that we could, build on that System Verilog base and have the methodology that we use for building your test bench. So way back when, like I said, in that first wave, there was something called Veracity, Specman, and they had something called E-code. And they created this ERM, E-reuse manual. That was, or maybe E-reuse methodology. That was kind of the first of these advanced methodologies. Synopsys came along with Vera a couple of years later. They created something called the VMM, the Vera Methodology Manual. That was a methodology for using Vera code and how you would build a test bench in Vera. As I said, in the late 90s, early 2000s, that's when System Verilog became a standard. And so what Mentor did is we looked at the other methodologies that were out there. We created something called the AVM, the Advanced Verification Methodology. And that was basically just a bunch of classes to build all the vanilla pieces for your test bench out of. You would then use class extension to make them specific to your test bench. Cadence had acquired Veracity at this time, and they basically took the ERM, which was all for E-code, and they rewrote it as the URM for System Verilog code. The problem was Synopsys was the gorilla, and they had 90% of the market share. AVM, built on some good things from these, but, we were having trouble competing with Synopsys. Cadence was in the same boat. They came to us. They said, hey, let's create a methodology together that we can go up against Synopsys with. And basically what we did is we took all the class library stuff from Mentor's AVM, and we took some of the coverage stuff from Cadence's URM and created what was called the open verification methodology. And we started winning. We started seeing both of those methodologies beating the VMM. Users started seeing value in the OVM over what you could do in VMM. And eventually Synopsys finally said, hey, we have to be in on this. So they up-revved the VCS so that it could run pure System Verilog code, and they joined the OVM. And that's where then the IEEE, the Accelera Committee, said, hey, this is good stuff. Let's make that a standard. Instead of calling it OVM 3.0, they renamed it the UVM. So that's kind of where all of these three-letter acronyms for verification methodologies came from, and the UVM is now an IEEE standard. It is supported by all three major EDA vendors. And so what really is the UVM is it is it's built on the System Verilog language. It will run on any System Verilog compliant simulator. And it's basically just a set of class libraries for things like drivers, monitors, scoreboards, checkers, and its vanilla versions of all these things are built as a class library. And then the user uses object-oriented class extension to, create their test bench out of these things. So it's a set of reusable building blocks. There is some thought to reuse from project to project that's built into that. And it's really, meant to be a way to simplify the whole manner of getting to a System Verilog constrained random test bench. The problem is it's still not necessarily all that simple. We've made it super powerful. So this basic structure of the UVM is that for every major communications port on our device, we create an agent to send and receive transactions over that port. So we've kind of split the test bench into up here is all at the class level and transaction level. Down here is where we pass those transactions. We turn that into bit wiggles to the device, monitor the bit wiggles from the device, turn that back into transactions, send that back up to our agent. Our agent will have a monitor. It will probably have a sequencer and a driver. So a sequencer creates a sequence of transactions. The driver sends those down here to the interface, which sends those to the device. The monitor monitors bit wiggles, sends that back. We have scoreboards. We have all these pieces. If we kind of look a little more at that, everything up here, as I said, is at the transaction level. So it allows us to do our debug at transaction level. So it's basically saying an AXI read with these parameters happened over this time period. If I need to, I can push down and look at the individual bit wiggles, but we can do a lot of our transaction at this higher, or a lot of our debug at this higher transaction. The other things, maybe we have a coverage collector, and that's going to be our System Verilog cover points, our System Verilog cover directives, cover assertions, all these different coverage objects that we can collect metrics about how well covered our device is with the coverage things. The scoreboard is there. So the problem with UVM is, even though it does, set up this methodology, set up all of these vanilla pieces for you, it's a lot of code and a lot of files. So every one of these agents is going to be maybe half a dozen to a dozen different files for that agent. So there'll be one for the monitor, one for the, for the driver. There'll be driver BFM. There's the sequencer stuff. There's all of these different things that you have to create for each agent. And even on that other test bench, there's 2 of these agents. So you double that. The environment is a bunch of files. The test bench itself, creating sequencers. And, so there's a lot to do. And for the average RTL designer, if you were not a C++ coder, if you were not a dedicated ASIC verification engineer, this can be a little bit daunting. And so I kind of like to say that, when you start to look at all this, you want to evolve past this first generation FPGA, and especially if you're an FPGA designer and you're just kind of coming back up this curve, you're trying to get to this System Verilog test bench, and it's not easy. So what Mentor did is we created this thing called the UVM Framework. And the UVM Framework is a couple of things. First of all, it's a simplification of all those classes and all the stuff in the UVM. So we've kind of even I wouldn't say dumbed it down, but basically simplified what you need to learn. Because one of the things with the UVM is there might be 5 or 6 different ways to do any task. So first of all, we simplified the classes, but second of all, and more important, we tried to hide as much of that code that you wouldn't be familiar with from you as possible. And so what we did is we've created this system where instead of creating those 15 files for each of your agents that I showed in the previous slide, you now create a template that basically says, you know, for my FPU interface, register interface, I've got a clock and a reset, I've got these ports that it has, maybe I've got a few variables that I'm going to use. And so you create this one line, 40, 50 line template, and you hand it that template to a code generator, which goes down and pulls all the boilerplate code that it needs from our UVM templates, grabs that thing, and then creates all of those class definitions, creates all the packages, creates everything you need, including the make file to compile that agent. So I go back and I create one of those templates for each agent. I create one of those relatively simple templates for my environment and for my test. And then what comes out the other end is a make file that I can just say make, and that will compile and actually launch that test bench so that you've done as little as possible and had to create as little code as possible. And then you just have a few tasks that you have to do. And they're tasks that a Verilog coder or VHDL coder will be more familiar with. So for instance, you know, you'll need to go into this driver BFM file. You actually can just search out this UVM change me within that file. And in this case, you know, when I want to send transactions, it puts in this generic access task, and I replace that maybe with a do write task and a do read task. And I just give, you know, I need to assign these variables. I need to wait a little bit of time, assign these variables, you know, et cetera. So you just give the signaling for that particular transaction. So maybe I do a do read and a do write in my driver. In my monitor, I'll go and do, you know, when I see this activity, I'm gonna, you know, get that. I create a couple of tests. And the real idea is that with the UVM framework, you know, normally you have to learn a whole bunch and you have to be pretty proficient with UVM before you're getting any useful simulation cycles. What we like to think is with the UVM, you don't really need to know a lot, and that test bench is created for you, and you can just do the tasks you need to, and you can actually be doing productive verification without needing to know everything about it. So the way I like to think of it is, I want to know how to drive a car. I don't need to know everything about how the internal combustion engine works to drive a car. So what we're trying to do is get you driving the test bench without needing to be a test bench mechanic. So what, you know, that did was it gave a methodology for somebody who is not an expert to be able to start to take advantage of system Verilog and UVM style verification. So the next step, I feel like, in that is that once we have this standardized methodology, we can start to create verification IP based on that methodology. So if you think about your current FPGA project, you've probably written a bunch of custom logic that's living inside that FPGA, but there's a good chance that the way you get to that custom logic is maybe through a you know, an Ethernet bus, through a PCIe interface, some serial ATA, maybe a UART. You might have, you know, a lot of IP now has AXI interfaces on it. So maybe I'm coming in through a serial ATA, that gets changed to an AXI. So to access my custom logic, If I just want to do a block level test bench on, say, this custom logic, I probably need an ASIC controller and some kind of a RAM controller. For this block of custom logic, maybe here, I might need PCIe and something else. So, and then if I'm doing chip level, I almost certainly don't have any custom interfaces. I'm using all pretty standard interfaces, and that's where being able to draw from a library of pre-created verification IP that is basically a UVM agent for a particular protocol, and that will then give me a full set of sequences that I can send as transactions over that thing to my DUT. So those sequences get turned into bit wiggles. It happens to my DUT. The information comes back. I get to debug all of this up at the transaction level. We have a full test plan for each of those protocols. So if you want to make sure that you've done certain operations, so let's say you're doing PCIe and you want to make sure that the thing operates in, Gen 3, and you can send certain type of transactions, you're not going to necessarily be testing the PCIe interface from your vendor, but you want to test that it'll work in Gen 3, that it's hooked up correctly, et cetera. So you can send those transactions, you can make sure you've tested what you need to, and it's all based on that standard UVM methodology. So this is the full collection of all the different VIP protocols we currently have. A couple of these roadmap ones may have actually been released by now. I'm not 100% positive where we are on some of these, but we basically sell it by the family. So if you're going to be doing Ethernet, you buy the Ethernet family. So you have one VIP protocol for each copy of Questa that you're going to be running test benches on. So if you want to simultaneously do 3 versions of the test bench to do different testing, you'd have 3 copies of Questa. You'd have 3 copies of the VIP Ethernet family. You can use as many instances of that. So if you have multiple Ethernet ports on your design, you only need one family to run a simulation. But if you're going to run multiple simultaneously, you would get multiple copies. So we have, PCIe is probably the biggest seller we have. That's the most people using it. Ethernet is a close second, I'd say. AMBA is a big one as well. We also have a memory library. So if you are using DDR memories in your design, and if your vendor is not providing a good model for those memories, you can pull these, drop them down, and they will act like a lot of different memories, a lot of different memories. So the way you use this VIP is we have a VIP configurator. You go through and you say, I want to do an AMBA bus. It has these parameters. I need to put down a memory bus. I need to put down different pieces. You configure each one of those with the configurator. That will output a configured version of that acts like what you need it to. Then you can instantiate that in your UVM test bench. To instantiate that in your UVM test bench, if you use that UVM framework that I showed in the previous design, you can instantiate these. What that configurator will spit out the configuration lines of code that you need to put into that environment template, so that you will drop down that particular UVM component and be using that in your verification. The next thing that I am going to touch on is, once you have started down this path, you probably want to start to look at doing some metric-driven verification. And what I mean by metric-driven verification is that you are collecting the coverage to be able to say when you are done. A lot of times with a directed testing approach, it's kind of an art. You kind of have to be able to say, hey, if I send this data, I think that this feature is covered. But it's always nice to have some metrics to help you with that. So Mentor's verification management system comes with our Questa Prime product. It is an add-on to our Questa Core product, and it gives a few facilities. So the main thing is that all the coverage information is stored in this unified coverage database. Once we're storing that coverage information in there, we can actually link that to your test plan and allow you to look at how you are doing on the coverage versus your test plan. It gives some trend analysis so that you can look at how your coverage is trending over time. The results analysis is all about debugging your whole regression suite simultaneously, as opposed to debugging each failing test. I'm not going to touch on either of these, but I will give a little more information on the test plan tracking and the verification run manager. So let me talk about that in a little bit, but first let's talk about the test plan tracking. So if we go back to this diagram that I kind of showed a version of earlier, are we done? How does it work? Well, what really facilitates it with our test plan, our verification management, is that how do you answer this question, are we done, and does it work correctly? And that is through linking the verification plan to that digital UCDB database that comes out of our verification engine. So what does that mean? And what that means is you write your test plan, and in this case, it's written in an Excel spreadsheet, and I've got kind of a section heading down here. I've got each different test that I'm going to run, a description of that. But then in these two columns, and I know you can't read it, I put in the name and the type of the linkage. So, this is an assertion with some name. This is a cover directive or a couple of cover directives with different names. Maybe I'll have cover points and cover groups. And so I put all that information about what objects within my code are connected to these different test plan objects. And then I can actually merge this test plan with the regression results. I think I have a better view of this on a later slide, but it gives me then a report which a project manager is going to be able to understand. I can write that report out as HTML, so he doesn't have to be a tool genius in order to use this. And we can do a lot of regression. So our test plan, as I kind of said, maybe you can read it a little more, is we have a section heading, we have the test that I'm going to run, a description of that test, and then the linkage to my coverage objects is built into my test plan. And then on the testing side, I'm going to create a bunch of tests, and maybe some of these are randomized tests with different seeds, maybe they're different tests. So I run this whole suite of different tests. Each one of those creates a UCDB, which has a certain amount of coverage. I can do things like merge and rank, so where I get a merged result with the fewest number of tests to get the most coverage. And then with that test plan linkage, I end up getting a report which shows, my test plan, my transmitter section, all the different tests I'm going to run on the transmitter. Here is my preprocessor section, my post-processor section. And, I can look and say, my transmitter right now is only 44% tested. Why is that? Let's drop it down. Well, I've done no testing on bonding mode 0 or 1. I've got 50% coverage on bonding mode 2, bonding mode 3 has 0% coverage. It's 0% because neither one of these cover directives has been activated or tested. CRC generation looks like I've completely tested all the objects within there. Maybe my frame counter, it says I'm 58%, and then I can look, why am I 58%? Well, it's because these different objects have different amount of coverage, and this all becomes a cumulative roll-up into the transmitter section. And then each section has its own roll-up into there, and then, you know, it rolls up to each section above it. And so right now, I can see that I've 80% covered my test plan. Well, I got to go cover those objects that aren't covered. So that's what doing metric-driven verification is about. Our verification run manager is, again, built into Questa. And, you know, a lot of times if you're running a regression suite, the normal thing is you probably create a bunch of either Tickle scripts or maybe Linux shell scripts or awk scripts. Python is starting to be used, but it's a lot of homegrown scripts that are all about how do you build and run your regression suite. So the verification run manager is basically about the same thing. It's about how do I compile my code? How do I build individual block tests? How do I build, you know, system level testing? Maybe these are some directed tests. These are a set of constrained random, so I'm using different speeds. So all the compile, all the build and run, and then as those finish, how do I merge them all together? And then how do I analyze what results I have, and how do I rerun failing tests for debug? As I said, you can do this all manually, but it gets more and more complex. The more and more complex your system is. If you use the verification run management system, it automates a lot of these tasks for you. A couple of the tasks that it automates is I'm going to run my regression suite. It's going to run each individual test. It will save away the log file from that test, the UCDB from that test, maybe any waves that I might have created from that test, and it saves it in a standardized location. You know, we have a lot of the process management there. And then what happens is, if that test passes, it automates the task of merging those UCDB results into a full merge. So the system knows when a test finishes it, I will take that and I will merge it with any other tests that have already finished. If that test, you know, if I then have a test plan, it automates that merging of the test plan. If it fails, it might say, you know what, this test failed. I was running this in a regression mode. Let's relaunch this test, but let's run it with all the debug flags so that this time I generate a full WLF database so I can debug what happened with that test. So that's just a touch on some of the stuff that the verification run manager does. It also, as sorry, didn't talk about this before, it creates that triage database. Down here, this automatically, you can set it up to automatically create the trend databases. So automating a lot of tasks that you need to do is what verification run management is all about. It is all about managing the process, the data, the tools, automating many of the tasks, relieving the burden, having a standardized database that you can go to our help group. So you can come to me, you can come to our customer support. If you built your test using the verification run manager, that really helps us to be able to debug you and get you up and running as quick as possible. So as I said, this is an option to Questa Core. It comes standard with Questa Prime. So if we look at our little graph here, we've now gone past system Verilog. We've added verification IP. We've added verification management. The last step that I'll talk about here today is our formal verification tools. So I've asked a lot of people about, what is, you ask people, and, what is formal verification? What's the difference between formal verification and simulation? So if you think about your DUT here, simulation is, I'm going to put some stimulus on this design, and I'm going to predict what the output should be. And because there are now registers in here, this design has state. And so by running a simulation, I start from reset, and I kind of wander through the state space of my design. Based on the stimulus I gave it, it tracks some vector through the state space. And then I run another simulation, and it tracks some other vector through the state space. Now, if there are flaws in my design, there might be illegal states that I would get into. And I have to hope that I send a verification vector that passes through those illegal states so that I can detect that they exist. So it's really based on the stimulus I sent, what was the response of the device, and did it happen to uncover any illegal states? What formal verification does is it starts from the reset state, say, and it calculates every possible state that the design could go into on the next clock cycle, and the next, and the next, and the next, and the next. And we can go a couple of million clock cycles into the future before the verification engine runs out of steam. And then what might happen is I've put on properties about that design that I want to test, and that's how I define illegal states. If the design goes into some state that violates one of the properties that I have stated about that design, it will then say, you've entered an illegal state, and this is how you get there. So this is the stimulus that you would put on that would get you into this illegal state. So that's formal versus simulation. The thing is, when formal property checking tools first came out, they are very high effort to write those formal properties. And it took kind of a formal expert to run those tools. And what we've done over the last 20 years probably is we've encapsulated a lot of this expert knowledge into what we call formal applications. So there's a whole lot of smarts that's baked in, and it uses that formal engine to try to see if your design maybe violates any of those properties. I'm not going to go through this whole slide, but basically, there are a lot of hard problems that are not easily solved via simulation, that if you're using a formal engine, it's much easier to tackle, especially things like the clock domain crossing problem. Those are almost impossible to detect in simulation because you really don't have metastability in simulation. They're impossible to solve in the lab because they are very spurious. They don't occur all the time. So CDC turns out to be one of the apps that really works. So this is the collection of all of our formal verification apps. We kind of split it into two different groups. One is general formal things, and then the other one is directed at the clock domain crossing problem. So first I'm going to highlight a few of the apps in the traditional property checking area, and then I'll go into a little detail about our CDC apps. So I'm going to talk more about AutoCheck. That's basically a bunch of checks that are baked into the tool, and you just compile your code and push go, and AutoCheck comes back with any issues you might have. The other one that I'll talk a little more about, I think, is the CoverCheck app. I'm not sure, but I just wanted to point out a couple others. SecureCheck is all about making sure that if you have protected regions of your design, that there are no backdoor ways to access protected data in your design. CoverCheck is about coverage closure. And then let's talk a little bit more about AutoCheck. So AutoCheck is a formal app. Basically, all you do is compile your RTL code. You use the same compile script that you would use for compiling for simulation. You might need to put a couple of things like what your clock frequencies are and a couple other things in a directives file. You push go, and it spits out, any issues that it might find with your code. So you don't need a test bench. You can run this at block level as soon as possible, and it's really about finding structural issues with your RTL code. So no test benches. You don't need to write any assertions. You basically just take your RTL code, run it through, and it comes back. If you have structural issues, it'll create a schematic. If you have state machine type issues, it'll create a state machine. If you have timing issues in your design, it might find, certain things, and it will generate a timing diagram that says this is an issue that you are likely to have. So it's, as I said, it's a one-stop push button formal check of your design. So there's probably 60 or 70 different checks that all RTL code should obey these rules. CoverCheck, as I said, is something for the coverage closure issue. So if you are in certain industries like civil aviation, automotive, they have very strict rules and they'll have governing bodies. They'll have what are called designated engineering representatives that you need to prove that your code has been sufficiently tested. And one of the things they want to see is code coverage. They want to know, if you don't have 100% code coverage, why don't you have 100% code coverage? So the normal way to do that is you would run your regression suite. You would look. If you have uncovered code, you have to go and say why, write waivers, etc. Or you have to say, you know what, I think that's coverable, and I got to go write some more tests that get me to that coverage. And you could spend a lot of time doing those two tasks. So what CoverCheck does is you go through that same front end, you run your regression suite, you get a UCDB, but then you turn that UCDB database over to CoverCheck with your code, and it will come back and it will either say, this code is uncoverable for this reason, and it will generate the waiver files for you, or it will say, this code is coverable, and here's the stimulus that you'd have to put on your device. This is a guide for writing the test to get that coverage in CoverCheck. So, like I say, it's a specific program directed at that particular problem. Clock domain crossing is the last thing I'll talk about today, I believe, and that is turning that formal engine towards the clock domain crossing tool. I mean, if you think about today's FPGAs and ASICs, they can be very complex. You might have one clock domain for your CPU. If you've got data coming in, from other sources over a UART or GPIO, those are going to be their own clock domains. You might have a USB on its own clock domain, an Ethernet, all kinds of different things that are coming in over different clock domains. And every one of those asynchronous clock domains, you now have a clock domain crossing, which means you will potentially have a metastability issue. So metastability is unavoidable in a digital ASIC. Anytime you are sending data from one asynchronous clock domain to another asynchronous clock domain, you have the potential that this signal will go metastable. And what that basically means is you hit the setup and hold window of this register, which would cause this output to go unknown. The way I like to talk about that in a relatable term is you are driving down the street, you're 50 yards back from an intersection, the light turns yellow, and based on your speed, you're not sure if you hit the brakes, you're going to skid into the intersection, or if you hit the gas, whether you're going to be going through that intersection after the light has turned red. And you find yourself in this moment of your foot wavering back and forth between the pedal. That is your brain going metastable. So how do you fix metastability issues? For every signal that crosses from one domain to another, you have to put in a synchronizer. That synchronizer could be really simple. To go from, a single bit from one domain to another, if you just put 2 flip-flops instead of 1, that's a single bit synchronizer. And what will happen is that first output from that first flip-flop may go metastable, but the second output, the second flip-flop, will make sure that metastability does not propagate forward into the rest of your logic. If you're passing a bus, now you can't just put those single bit synchronizers. You have to get a little more complex. Maybe you put, a mux and you say, I'm going to hold the value in the receiving flip-flop until I get the signal that it's safe to sample, et cetera, et cetera. Well, now you have a timing protocol. You have to make sure that bus is not changing the entire time that control signal takes to get over, get received, and go away in the other domain. So now you have a timing protocol. So what a good CDC solution does is first it does the structural analysis for every signal that's crossing from one domain to another. And it makes sure that there's a synchronizer in place, and it makes sure that synchronizer is of the proper type. There are a number of tools on the market that do this step. Even, say, Xilinx and Altera, they provide some clock domain crossing analysis that does a fairly decent job of this first step. The second step is that you need to make sure that not only do you have the right kind of synchronizer, but that the circuitry that drives this synchronizer and drives the logic to and receives, that all of that circuitry is properly handling the handshake protocol to send the data from one domain to another. And so that's doing a temporal protocol analysis on all the circuitry to make sure that you can't have timing errors with that circuitry. This is where it gets complex, and the vendor Xilinx Altera tools do not do this piece of the analysis. There's a couple other tools that do an okay job of this. The last piece that you need to do is, if you look at this diagram, you'll see I've got this path right here. I've got a synchronizer. I do protocol analysis. I say that's all okay. I've done both these steps. I'm good to right here. Now I'll do the same thing up here. I'm going to pass this. There's a proper synchronizer. I can't violate the protocol. I'm good to right here. But if you look, these two signals are individually good, but they'll go through maybe some sequential logic and then eventually come back together through this combinatorial cone of logic. And the question is, back here in clock domain A, these two signals had some kind of timing relationship with each other. Maybe they were both generated on the same clock edge. Well, the problem is, because I've gone through this synchronizer, that by the time you get to here, these signals could be plus or minus 1 cycle out of phase with each other. And is that a problem when it comes back together through this logic zone right here? And so that's what's called reconvergence analysis. And so our Quest to CDC tool does all 3 of these steps, and we are, I guarantee you, the only solution in the industry that's doing a full analysis of all 3 types of problems. And so what happens is you run your CDC analysis, it will detect a whole bunch of paths that it says, hey, I've looked at these, they're good, there's no problem. It might come up with a whole bunch of paths that say, these have violations, and that's where it will show these structural violations. You get to look at the code, you get to look at all kinds of things. You might have some of these cautions. And so this is probably that first static check. This is definitely that first static check. And so I've got a whole bunch of things you need to fix, but then these, I now use my test bench and I start to do some more analysis to say, do I have protocol violations on these? And so I can run the protocol analysis and I'll either promote some of these to passes, or I'll find violations, I'll throw them up into there. And then you do the reconvergence analysis. So all of these different steps, and you want to get it to the point where you have no cautions, you fix all your violations, and you get everything to be evaluated correctly. So this is just the CDC analysis. So right here, the reconvergence analysis. So I've got a couple of proper synchronizations that happen. I go through one level of flip-flops, they come back together. What our tool does is it uses your test bench, it injects jitter, and then you can solve your reconvergence issues that way. So if you're in the automotive industry, they have a standards body called ISO 26262. We are the only CDC and only other formal engine that has gone through certification for use in the automotive industry. We got this certification over 2 years ago. There is no other CDC solution in the industry that has been certified by the ISO 262 board. So that's just kind of one way that I can back up my statement that we're the most thorough CDC solution in the industry. So what are the benefits of our formal verification solutions? I feel like they help to reduce risk. They are more efficient in the sense that they are doing a full state space analysis. They're quicker and easier to use than writing your own properties in formal. And they're very complementary to what you do in simulation. You can start to use these before you have a test bench. And so that kind of takes us in our little evolution graph here to formal verification. That is where we are today. Obviously, verification continues to evolve, and we'll have to see what the next 10 years brings. So a couple of useful links that I'll put out here. And it's this first one is the one that I think is the most important. This is the Verification Academy. Let me see if that actually will bring it up. Yeah. So the Verification Academy is a mentor-sponsored education website. It is free, so you don't have to pay anything for it. It has a whole bunch of courses on different topics, all the way from just simple, I am doing block level testing and I want to go to a more metric-driven flow to a more process-driven flow. That's this evolving FPGA verification, all the way up to everything you need to know to write your first UVM test bench to how do I create a really advanced UVM test bench. Portable stimulus is probably the newest course that's out there and has a lot of buzz in the industry. So I really highly recommend you come and take a look at these courses on Verification Academy. There's also a whole online reference manual for UVM in general. And then there's a forum for asking questions, and we have a lot of our experts that take a look at that forum all the time. So a couple of useful links there. And then basically at this point, if there's any questions that I can answer,